Okay, last time we were talking about covalent compounds in the periodic table. And how are we going to put them together? Hydrogen has one valence electron, so hydrogen tends to form one bond. Carbon has four valence electrons, so carbon will form four bonds. Nitrogen has five valence electrons. It forms three bonds with one lone pair. Oxygen has six valence electrons. It tends to have two bonds, two lone pairs. And the halogens, fluorine, chlorine, bromine, and iodine, form one bond, three lone pairs, and seven valence electrons. We'll get in how to do Lewis structures. It's fairly simple. Heard that before. Okay. A Lewis structure, well, what is it? Well, a molecular formula tells you what the atoms are, what the elements are in a molecule, and how many of each. Water, H2O, tells me I have hydrogen, oxygen, two hydrogens, and one oxygen. What it doesn't tell me is how they go together. So a Lewis structure shows me how they go together. Okay? So, those are some general rules for drawing Lewis structures. I'm going to give you my interpretation of it. I give you a molecular formula. You have to determine the total number of valence electrons in the molecule. I'll show you how to do that. We'll do some examples. 2, place the terminal atoms around the central atom. That means we're going to put atoms around the central atom. Put a single bond between the central atom and each terminal atom. A single bond is how many electrons? 2. Give each terminal atom a complete octet, except for hydrogen. Hydrogen only needs how many to be happy? 2. If you have any electrons left over, you put them on the central atom. If the central atom needs additional electrons and you don't have any left, you have to borrow them from the terminal atoms. The idea is everybody gets 8, the octet rule, except for hydrogen, which needs 2. Sounds complicated. We're going to do a couple examples. You'll see it's fairly straightforward. I know, heard that before. Oh, insert blank page. There we go. So, start with blue. Let me start with something fairly simple. Water, H2O. We have to look and see how many total valence electrons. Hydrogen has how many valence electrons? Hydrogen has how many? 1. This is in column 1. How many hydrogens do we have? 2. So 1 valence electron times 2 hydrogens. So we got 2 from the hydrogen. We have 1 oxygen. How many valence electrons does oxygen have? 2. No. What column is oxygen in? I'm talking about charges. How many valence electrons? 6. It's in column 6A. So it's 6 valence electrons for a total of 8. That's how many electrons we have to work with. No more, no less. Oxygen is going to be the central atom. Hydrogen is never a central atom because it can only have 1 bond. So, I put the oxygen in the middle, surrounded by hydrogens. I just do this to make it look symmetrical because I like symmetry. The next step, draw a single bond between the central atom and each terminal atom. Here's a single bond. Here's a single bond. Single bond is how many electrons? 2. So how many have we used? 4. How many we got left? 4. We had 8. We used 4. We got 4 left. Okay. Hydrogen needs how many to be happy? 2. Well, it has 2. So it's in the middle, it gets shared. So this hydrogen has 2, this hydrogen has 2. I can't put any more electrons on hydrogen. I have 4 left over. Where do they have to go? On the oxygen. And he put them in pairs. There. So that's oxygen. That is water. Everybody's happy. Oxygen now has 8. 2 lone pairs, that's 4, and 2 single bonds, that's 4. That wasn't so hard. Right?
And do you write it like that with a line, or do you put the...
You usually put lines for the bonds. Bonds are lines, dots are lone pairs, non-bonding electrons. Okay, let's look at carbon dioxide. Tell me how many total valence electrons there are. I'd say quick, but obviously it's past the time for quick. Oxygen has how many? 6. It's in column 6. 6 times 2 is 12. Carbon has 4. 12 and 4, 16.
I was doing 6 and 4. I was doing multiplication.
Well, you got 2 oxygens, so it's 6 plus 6 plus 4. You got to take each individual atom. So I have 16 electrons to work with. Carbon, in this case, is the central atom. The least electronegative atom is the central atom. So we're going to put carbon in the middle, and oxygen in the terminus. What's the next step? Same bond. How many have I used? 4. What's the next step? Give each terminal atom a complete octet, except for hydrogen. Hydrogen only needs 2. The oxygen needs 8. Needs an octet. It already has 2. 1 oxygen. Each atom. This oxygen has 2. This oxygen has 2. Okay? We've used 4 electrons, but each oxygen only has 2. So I got to add 6 to each. So now each oxygen has how many around it? 8. How many have we used? 16. I've used all the electrons. Is everybody happy? Really? How many does carbon have around it? Carbon has 4. 2 single bonds. That
So it needs 4 more?
it needs 4 more. I don't have 4 more. I've used all 16. I got to get them from the terminal atoms. I'll take 2 from this oxygen, 2 from this oxygen. So now I have now carbon has 8. Each line is 2 electrons. This is a double bond. So we got 2, 4, 6, 8 for the carbon. And each oxygen has 8. 2, 4, 6, 8, 2, 4, 6, 8. So carbon dioxide has double bonds. Single bond is 2 electrons. Double bond is 4 electrons. Triple bond is 6 electrons. Just look at it as each line represents 2 electrons. All right? Does everybody see what we're doing here? Yes, ma'am.
So both of those diagrams either rectangle or just the bottom?
Bottom one. Because the top one, the carbon doesn't have 8 around it. You got to keep going until you get everybody happy, so to speak. Okay, let's look at a couple more. Let's change the grid. Hydrogen cyanide. How many valence electrons? Quick. Oh, I said quick. No. Hydrogen has how many valence electrons? 1. Carbon has how many? 4. 1 and 4 are 5. Nitrogen has how many?
3.
No. 5. 5 and 5 are 10. Remember, the valence electrons are the same as the column numbers. Nitrogen has a charge of -3, but it has 5 valence electrons. So now I have 10 electrons to work with. Carbon is the central atom. Nitrogen here, hydrogen here. Next step. Put in what? Bonds, single bonds. Next step, I got to give everybody a complete octet except hydrogen. So hydrogen's happy right now. So I give the terminal atoms, the only other terminal atom is nitrogen. So nitrogen has 2, it needs how many? More. 6. There, now nitrogen has 8, hydrogen has 2, so a total of 10. We've used up all my electrons. What about carbon? Poor old carbon. It has 4, so it needs what? Where is it going to come from? It has to come from nitrogen. Those are the only atom that has electrons. So take 2, 2. Now we have a carbon-nitrogen triple bond. So now nitrogen has 8 around it. Carbon has 8 around it. Hydrogen has 2 around it. It's not fair because what?
Well,
Go ahead.
I was thinking that it's not fair because you're taking it from the nitrogen, but when you put it right there, then it's for both of them.
Yeah, when they're shared, they count for both. Anything in between counts for both.
So,
Yes.
like,
Yeah. Nobody's unhappy. Unlike life, which isn't fair, except for next month. Next month is fair. State fair in October. Okay. Yes, ma'am, and back. Octet rule. Everything has to have 8. All right, so you follow those procedures. You start with single bonds, then you give the outside terminal atoms, you give them complete octets. So you put nitrogen gets an octet, make it 8. Hydrogen only needs 2. That's the exception. So hydrogen needs 2. We're done there. Well, then carbon only has 4. Okay? So carbon needs 8, so it needs 4 more. It can only get unused electrons. The only terminal atom that has unused electrons is the nitrogen. It has 6 of them. So it gets 4 from the nitrogen. So that gives us a triple bond. So now everybody has 8. 2, 4, 6, 8. 2, 4, 6, 8. And hydrogen has 2. Yes?
how do you determine which one is the single atom?
It's usually the least electronegative. And if you look at a periodic table, as you go across a row or a period, the electronegativity increases. If you look at a column, as you go from bottom to top, electronegativity increases. So if you disregard column 8, the most electronegative element is fluorine. Because it's the furthest one to the right, and it's the furthest one at the top.
But we did hydrogen first because it's not. Because you said you would do the least one. It's normally the least one.
Yeah, but hydrogen is never a central atom because you only have one bond. Okay? Let's do a couple more. As you do these, you find out it's, well, at least for the ones we're going to do, it's pretty simple. You follow the steps. All right, let's pick another color. Okay. Sulfur dioxide. How many valence electrons? Quick. Yeah. Sulfur and oxygen are in the same column. They're all in column 6. They got 3 total atoms. 3 times 6 is 18. There. Which one is more electronegative, oxygen or sulfur?
Oxygen.
Oxygen is more electronegative because it's above sulfur. So the least electronegative one is sulfur, so that's going to be in the middle. I can put sulfur in the middle. Oxygen is the terminal ones. Next step. Single bond. Always a single bond. Stop trying to jump ahead. Now what? Make the terminal ones have octets. They already have 2, so I'm going to add 6. Okay, how many electrons have I used? 16. You don't have to count. If I made each one an octet, there's 2 of them. 2 times 8 is 16. Okay. How many did I have to work with? 18. So how many got left? Where am I going to do them? Can't put them on the oxygen. I have to put them on the sulfur. There we go. Used all 18. Is everybody happy? Who's not happy?
So,
It needs how many?
2 more.
Where am I going to get them from? They got to go in pairs. Just from one oxygen. Okay. Which one's right? This one or this one? I mean, they both all have 8. Top one I borrowed 2 from the one on the right. Bottom one I borrowed 2 from the one on the left. Both of them. They're equivalent. They're what's called resonance structures. Sometimes you'll see them with a double arrow. What it really has is one is not a single bond, one is not a double bond. It flip-flops back and forth between the 2 so fast that it's an average of the single and double bonds. So either answer is correct. Yes?
How did you get 18?
How did I get 18? Sulfur's in what column? That's 6. Oxygen's in what column? 6. 2 oxygens, 6 and 6 is 12. Plus 6 from the sulfur is 18.
Oh.
Yes?
So for the top one, on the right of that oxygen, we have the 2 dots at the bottom. So did you?
Count. 2, 4, 6, 8. Oh, here I put them on the bottom?
Yeah.
You can put the lone pairs anywhere.
Oh,
Okay, it doesn't have, it's not like,
I got a question. Why did you make that a double bond on the...
here,
Yeah.
I borrowed these 2 so it goes in between. Every time you put 2 electrons in between, it's a bond. We already had a bond, so we added another line, so that makes it a double bond.
Did you say the double bond except for everything?
Yeah, S didn't have 8. It needed 2 more, so I had to borrow them from one of the oxygens. Didn't matter which one. So if you've drawn it, like top one or the bottom one, either one is correct. Don't worry about that. All right? Okay. Let's do a couple more. We have to move on. You guys are getting this. Oh, we did SO2. Let's do SO3. Sulfur trioxide. Quick, how many valence electrons? 24. That shouldn't have taken you long because you did SO2, which is 18. We're adding one more oxygen, which is 6. 18 to 6 is 24. That's okay. So it shouldn't have taken you that long. Okay, sulfur surrounded by oxygen. No, it wouldn't matter if I put the oxygen on top. Next step, single bond. Next step, make the terminal atoms have a complete octet. How many electrons have I used?
24.
24, very good. So I've used all my electrons. There, everybody's happy, right? Who's not happy? Sulfur's got how many?
6.
It needs what? I know, but needs how many more? Where's it going to get it from?
Any one of the three.
Any one of the three, it doesn't matter. So let's take it from the bottom one just because it looks better. Now everybody's got 8. Okay? So you just think of it as kind of a puzzle. You know how many pieces you have, and there's rules for putting it together. And if you follow the steps, it's really not that hard. One more. Let's go for a biggie, okay? Let's see if we can really mess things up here. Silicon tetraiodide. How many valence electrons? Quick. That's kind of the question. So what?
24?
32. Iodine's in column 7. 7 times 4 is 28. Silicon's in column 4. 4. 28. 4 is 32. This is going to take forever. 32 electrons you got to put in. I'm never going to figure this out. Okay. Silicon's the central one. Surrounded by 4 iodines. Next step, single bonds. Next step, octet. There we go. How many electrons have we used? 32. So we used up all our electrons. Everybody happy?
Yes.
Yeah, we're done. Well, it didn't take long to do that, did it? So, carbon's got 8. Each iodine's got 8. We're done. And I bet you thought it was going to be hard. So you need to know how to do this for the next step. I love that laugh. It's like, oh, the next step. You're just setting us up. No. I wouldn't do that. Okay, that goes through the procedure. Oh, that goes more through the procedure. That's the one with the double bond. Okay. Let's go back to full screen, which is this one. Naming covalent compounds. Remember we said we use prefixes. NO2 is what? NO2 is what? Prefixes. No. Name the compound. What is CO2?
Nitrogen oxide.
No, what is CO2?
Carbon dioxide.
So NO2 is
Nitrogen dioxide.
nitrogen dioxide. Prefixes, that means you do the subscripts. N2O4. What's the prefix for 2? Di, the name of the element, dinitrogen. Prefix for 4 is tetra. Dinitrogen tetroxide.
Do we do this?
We didn't do this? Okay. Well, we're actually starting. How do you name this? When you do covalent compounds, you use prefixes. So you name the first nonmetal. Remember, covalent compounds are 2 nonmetals. First nonmetal by its element name, and the second using the suffix IDE. Okay? So here it's nitrogen. If the subscript is 1, we don't use mono. CO, carbon monoxide. Let me look at, here we go. These are the prefixes. 1 is mono, 2 is di, 3 is tri, 4 is tetra, penta, hexa, hepta, octa, nona, deca. What? You've used all of these prefixes before.
Geometry.
What?
Geometry.
Well, no. What's that big government building in Washington? The Pentagon. Is there some secret building in? Is there some secret building in Washington I don't know about? The Octagon?
You know, there's enough people looking at there. Come on now.
Oh.
Tell me what age that's on.
98 and 97.
Wow. Government conspiracy. Octagon. A 3-wheeled vehicle is called a tricycle. Okay. We don't have an octacycle. Okay. All right.
I would think hexa would be 8.
Hexa is 6.
Oh, that's right.
Octa is 8. Let's talk about octet rule. 8. Okay. NO2. If the first subscript is a 1, we don't put. It's not mononitrogen. We leave the mono out. So it's nitrogen dioxide. Remember when we did ionic compounds? They all ended in IDE. These all end in IDE too. Here we have a 2, so it's dinitrogen tetroxide. CCl4, carbon tetrachloride, which is what they used to use to do dry cleaning with until they found out it was carcinogenic. So they replaced it with a different chlorinated hydrocarbon, which is also carcinogenic, but not as carcinogenic as carbon tetrachloride. I don't dry clean.
Why?
Why?
This is what I just said.
That's what I just said. It's carcinogenic. Unless you find one that uses supercritical CO2. But, no, we're good. So let's do a couple. And see where we're going with this. All right. Let's see. OF2, what would that be? Di something. Okay.
What's that?
I don't know. Gonna have a periodic table? Oxygen difluoride. So if I gave you a name, you should be able to tell me the formula. Nitrogen, if I said nitrogen monoxide, what would the formula be? No.
NO1?
No.
N-O.
No.
No, N-O.
NO.
N-O.
No.
No, he's right. No.
That's right. No.
No.
No. No.
So then why would you say
Monoxide?
why would you say that?
Because you use the prefix, the mono prefix for the second one. Like CO is carbon monoxide, it's not carbon oxide.
So it's happened to other one. Another one.
And when you use, when two vowels like tetra, P2O4 would be what? Diphosphorus.
Diphosphorus oxide.
What's four? Tetra.
Tetraoxide.
Not tetraoxide. When you have two vowels together, you lose the first one. It's tetroxide.
Is that TR? That
TETR.
Thank you.
Yeah.
Tetroxide.
The prefix is tetra.
Oh, so you dropped the A. Okay.
You always use it. But,
Are we using another person because they have a number?
yeah, it's two. Tetroxide, you get rid of the A. So it's tetroxide. Okay. SCl2. Sulfur dichloride. So doing covalent compounds is pretty simple. You just use the prefixes. Yeah.
No, I was waiting for the but.
But okay. There's no but. So we did ionic compounds. Now we've done covalent compounds. Here is a chart, a flow chart for doing nomenclature. It kind of gives you, if I give you a compound, how do you name it? Start at the top. You have to make a decision. Is it ionic or covalent? Okay, if we're two nonmetals, or a nonmetal and a metalloid, it's covalent. you use prefixes. So CO2 would be carbon dioxide. So we're done on the covalent side. If it's ionic, then we have to make a few choices. If it's a transition metal, a metal with more than one possible charge, use the table in your book, we have to use the cation name, which is the name of the metal, the Roman numeral, which is the charge on the metal, and then the anion plus IDE. Example would be FeCl3, iron 3 chloride. If it's a main group metal, or silver, so main group metals, column 1, column 2, column 3, bottom half of column 4, well, bottom half 4 has multiple charges. Use the cation plus the anion, stem plus IDE. So there would be NaCl would be an example of sodium chloride. If you follow the flow chart, you should be able to tell me how to name it. He says.
Is that flow chart in the book somewhere?
No.
Go on.
I'm not that.
What are you saying when you're saying cation?
Cation. That's the metal. Metals become cations. They become positively charged.
And then it says
Anion. Where? Here?
Yeah, at the end.
Cation,
in the middle.
Roman numeral.
No, in the middle, at the end.
Cation plus the anion stem plus IDE. The anion stem. So instead of chlorine, it would be chlor. Chloride, bromide, sulfide. For the cation, you use the full name of the element.
What's the whole point of that? Like, I don't.
If I give you a compound, ask you to name it,
Uh-huh.
you
Okay.
need to know how to name it.
By looking at it.
Uh-huh. For example, plus anion
Yeah, what's it say?
stem plus IDE. The stem of the anion name.
Stem plus I,
IDE.
Plus IDE.
stem plus, yeah, that's what, okay.
So if I look at one of these, let's see, do an example. BABR2. Let's just follow the flow chart. Is it ionic or covalent?
Ionic,
Why?
because it has a main metal.
It has a metal. All right. Is it a transition metal or a main group metal?
Main metal.
Main group metal. So now we're over on the right side there. So how do we name it? We name the cation, which is the full name. What's the full name of the cation?
Barium.
Barium.
Excuse me.
The anion, which is bromine, so its stem is brom plus IDE, barium bromide. Okay?
But you don't have to put two,
Do I have what?
put two,
No.
put down.
No. Dyes are used with covalent, prefixes are used with covalent compounds, not with ionic compounds. That's why I put the chart up there. Follow the chart. Let's look at another one. All right. Pardon? I can't hear you. What about it?
Is this chart in your PowerPoint?
No. Well, it's in mine, but it won't be in the ones I posted, because these are SmartBoard. Post SmartBoard. So, CuCl2, ionic or covalent? Great. What? So it must be ionic. Copper transition metal? Look at periodic table, you should be able to tell. It's transition. So I could have more than one charge. So what do I need to use? What? Roman numeral. So I named the cation, which is
Copper. Copper 2 chloride.
yes, copper. Copper in this case is a charge of +2. Chloride.
Can we do another one? Because I was right there.
You can do a couple more. Sorry, what? Two nonmetals are covalent, or nonmetal and a metalloid. So, PCl3, ionic or covalent? Why?
Non-metal.
Two nonmetals.
The way we just put on
B.
phosphorus trichloride.
Phosphorus trichloride.
So you said a while ago that we didn't have to put that tri thing in there because,
Oh, all their compounds I gave you were all ionic, so we're on the left side of the chart. This was covalent, now we're on the right side of the chart. Right side of the chart, covalent, we use the prefixes. PCl3 is covalent, not ionic.
Step to the side.
You have three situations. You have one non-metals, one that has transition metals, or one that has two non-metals.
Yes.
On top of the chart.
So the arrow that's pointing that way, that you see off the down this way, okay, main group metals plus, and then.
Plus silver. Okay? So you have three choices when you name something. If it's covalent, you use prefixes. If it's ionic, no prefixes. If it's ionic, a main group metal, it's the name of the metal plus the anion IDE. If it's a transition metal, or on the chart in your book that has multiple charges, it's the name of the metal, the charge on the metal in Roman numerals in parentheses, and then the anion IDE.
Okay, you write that down for me.
It's right there.
It just sounds more in order when you do it like that, instead of me having to guess.
Okay. So here we got. If it's covalent, these prefixes. If it's ionic,
Main.
main group metals. It is the cation, which is the metal name, plus the anion stem, plus IDE. We have ionic. Metals with, see what a line means, with multiple charges. It's the cation, again, which is the metal name. The Roman numeral in parentheses. It's the charge of the cation. Then the anion stem plus IDE.
Is that the transition?
Any metals with multiple charges. So it's mostly the transition. It's also column 4, tin, and lead. But it's not all transition. So there's a table in your book that has all the ones with the multiple charges on them. So to know where that table is. There, is that better?
Yes.
Okay. Ionic, and in parentheses, main group metals. How do you name them? You use the cation, which is the metal name, plus the stem of the anion, plus IDE. So if the anion was iodine, it would be iodide. If it was oxygen, it would be oxide.
That's, you know, being the short version of the name.
Yeah, stem means the short version of the name. Where were we? Can I switch this?
No.
Write faster. Okay, we've learned how to do the Lewis structure. Now we have to determine the shape of the molecule. So we know how it goes together, we have to know what its shape looks like. Remember we did the experiment with the smells, which depend on the shape of the molecule. So how we use this, how do we do it? Molecular shape is done, at least in this class, with a theory called the Vesper theory, which stands for the valence shell electron pair repulsion theory. Pretty simple. I know you doubt me. Don't doubt me. Okay? So, you have to determine how many groups come around an atom, central atom. The Vesper theory helps us determine the shape. Here we have very expensive atomic models.
Does anyone
So-
make that bigger?
Yeah, I don't know if I can go back this way, go back this way, go back this way. There you go. All right. So, the theory says, when we did the Lewis diagrams, the electrons were in pairs, right? Charge on electrons are negative. So do they want to be next to each other? They repel each other. So, we're looking at the valence electrons and how they're going to repel each other. They don't want to be near each other. So here I have a central atom. I stick an electron pair in here. So, I want to put another pair in. It wants to be as far away from this pair. Where do I put it?
Opposite side.
Opposite side. I'm going to extend this page. So here I have the central atom. So I have one pair. I put the other pair here, opposite side. What is that angle?
90 degrees.
Try again.
Linear,
Angle.
180.
180. 180 degrees. What's that shape?
Linear.
Linear.
Like the first time I said it,
Now, I want to put 3 electron pairs as far away from each other as possible. Okay? So I have 3 of them as far away from each other as possible. What are those angles?
Trigon.
What is the angle? The
Oh,
number?
120.
120. What shape is this? Like triangle. If I turn it on edge, they're all in the same plane. That means it's flat. So we describe this as trigonal, planar. All right. So far, so good. I want to put 4 of them as far away from each other as possible. How far apart can I put them? No. 90 works in 2 dimensions. Turns out 3 dimensions. You can put them 109.5 degrees apart. That's how you draw something that like this as well.
What are those numbers you wrote? I'm sorry.
109.5.
Okay? So, there's a description for this. Prefix for 4 is tetra. And each side is called a hedron. So this is tetrahedral. Okay. Anything complicated about what I did? There's the Vesper theory in a nutshell.
What does it go up to?
What?
What does it go up to?
Well, it goes past 4, but we're not going to go past 4. There's a couple more. We're not going to get into octahedral and hexagonal and so, let me get rid of this. Let's look at CO2. Thing you have to remember, we have to look and see how many groups are around the central atom. What makes up a group? So a group is equal to a single bond or a double bond or a triple bond or a lone pair of electrons. All of those make up a group. A double bond is a single group. It's the same as a single bond. A lone pair of electrons is the same as a single bond or a double bond. They each constitute a group of electrons. It's not like a double bond is 2 groups and a single bond is 1 group. No, they're each a group. So that's the important thing to understand. So if we go up here and look at CO2, how many groups are on the central carbon? 2. We've got a double bond and a double bond. So there's 2 groups. And we said we arrange 2 groups how far apart?
180.
180 degrees. So the shape of CO2 is
Linear.
linear. All right. Let's look at a couple other here. Let's look at water. We do waters, and we did it, Lewis diagram. How many groups around the oxygen? Try again. 4. 2 single bonds, 2 lone pairs. 4 groups. How do 4 groups arrange themselves?
4 9.5.
Tetrahedral. Now we got to look, so that's the electronic arrangement. To get the molecular shape, we have to look at where the atoms are. So I have 4 groups. How many of those groups have atoms on it?
4.
Really? Is there an atom attached to this lone pair? 2 groups. 1 hydrogen, 1 hydrogen. So this is what it looks like. We don't see those lone pair. We can't physically see them. We can see where the atoms are attached. We can't. So what shape is this? Bent. We took a linear molecule and just bent it. Water is bent.
Where's that at? in the book?
So water is actually bent. Okay? Let's look at one more. Let's look at ammonia. Let's do ammonia's Lewis structure. How many valence electrons? Sure. You guys should be learning where all these
8.
8. Nitrogen's in column 5. So we have 8 electrons. There's my single bonds. I've used 6. I got 2 more left over. Where do they go? On top of the nitrogen. How many groups are on the nitrogen?
3 groups. 4
No.
groups. 4
4
groups.
groups. 3 single bonds and a lone pair.
I didn't see the last one.
4. So the electrons are going to arrange themselves as a tetrahedral, but only the 3 of them are going to have hydrogen atoms. Okay? So now it looks like this. We don't see the top part. So there's a name for this, and we said we have 3 things. It's trigonal, but it's not in a plane. It's not flat. These are below the nitrogen. So if I think of 3 sides that are connected on an angle, I think of something in Egypt, pyramid. So this shape is trigonal, pyramidal. So it actually looks like so those different shapes give different properties to the molecules. So you can kind of envision how something that's bent would function differently than something that's flat. Something that's linear would function differently than something that's pyramidal. Yes,
So give me an example of a bent form of H2O.
that is. H2O is bent.
I know, but like, what, like when you, when it
All
changes
water is
forms,
bent.
like when it changes forms? and
No,
stuff
it's all
like that.
bent. The molecules are always bent. Has nothing to do with the form. It's bent. The molecule is shaped as bent. So there's a trigonal planar. If we look at formaldehyde, even though we have a carbon-oxygen double bond and 2 hydrogens, we only have 3 groups. We have a double bond and 2 single bonds. 3 groups. They all have bonds attached to them. Trigonal planar. So formaldehyde is trigonal planar.
So the emergence is linear, trigonal planar, and then the
Tetrahedral.
and triangle. Is that the ones that we need to?
Yeah, there's a table, and I'll show you how easy it is to figure it out. 4 tetrahedral, so methane is tetrahedral. These are all on your PowerPoint slides. Ammonia, which we talked about, is tetrahedral, but one corner of the tetrahedron is that lone pair I talked about. We don't see that, so it ends up being trigonal pyramidal. Remember, we can only see groups that have atoms attached to them. We can't see lone pairs of electrons. And water, again, has 4 groups, 1, 2, 3, 4. 2 of them are lone pair, so it is a tetrahedral shape, but we don't see the 2 lone pair, so water is bent. You can't straighten. That's the way it exists in nature. All right. There's a table in your book. If you have 2 groups around the central atom, and an atom attached to each group, it's linear. If you have 3 groups with 3 atoms, no lone pairs, it's trigonal planar. One that they didn't put in there is 3 groups, 2 atoms, 1 lone pair. It's bent. Okay? So there's 2 choices for 3 groups. One is trigonal planar, one is bent. If you have 4 groups, and every group's attached to an atom, it's tetrahedral. If you have 4 groups, 3 of the groups are attached to atoms, 1 lone pair, it's trigonal pyramidal. If you have 4 groups, 2 of the groups are attached to atoms, if you have 2 lone pairs, then it's bent. So there's 2 ways you can get bent molecules. 3 groups with 1 lone pair, 4 groups with 2 lone pair. There's only one way to get tetrahedral, there's only one way to get trigonal pyramidal.
4 groups with 2, what's that called?
Bent.
What, the degrees for the one you just scribbled in there, the bent, 3, 2, 1?
It's actually a little bit less than 120.
That's the what's confusing. That's the 120.
Okay?
Can you go over all the 2 choices and 2 groups? You said 4 groups, each group attached to an atom and 1 group.
Mean for the 4s?
Yeah, you said there was 2 choices for 2 groups, right?
There's 2 choices for bent. You can have 3 groups around the central atom with 2 atoms attached and 1 lone pair. That'll give you a bent. You can have 4 groups around a central atom, 2 lone pair, 2 atoms attached. That'll also give you bends. Just put them away. Yes? Three groups, 2 atoms, and 1 lone pair. That's the only one that's not in the table. Electronegativity and bond polarity. This is a table of electronegativity. And I said you go from left to right across a row, it goes up. And in the column, as you go from bottom to top, it increases. What does this have to do with anything? It has to do with the fact is how polar a bond is. If you have on a bond 2 same atoms attached, it's nonpolar because they're both competing for that shared pair of electrons. They're both pulling with the same force. There's no polarity. Or even if it's slightly different, 2.5 and 2.1 is considered nonpolar. If you get a big difference in electronegativity, you get a polar covalent bond, or what's called a dipole. You look between the carbon and the oxygen electronegativities, and that table's on page 102, 103, 102. Oxygen is 3.5, carbon is 2.5, so it's a difference of 1. That results in what we call polar covalent bond, unequal sharing. What happens is the carbon, the oxygen wants the electrons more than the carbon does. So think of it as a tug of war. So it's pulling with much more force. So if I look at the electron distribution, it would favor the oxygen. It doesn't pull them completely away because that would be a transfer of electrons. That would be ionic. It's still sharing them, but most of the time the oxygen has them. So remember an ionic bond, when we do a transfer, we get a positive and a negative. Well, here we don't get a full positive or a full negative. We get a partial. So the oxygen gets a partial negative, that's what that little delta sign means, and the carbon gets a partial positive. So if you think of a magnet as a north and south, what do we call them, north and south? Poles. So how many poles are in there in a magnet? 2. What's the prefix for 2? Di. We form a dipole. So that's all that means. Think of it like a magnet. So it now has a charge. It's a plus N and a negative N to it. So if you look at the E and D differences, remember I showed you a little video, ionic or covalent? We talked about E and D differences. If it's less than 0.5, it's considered nonpolar. If it's 0.5 to 1.9, the difference is polar. They still share. If it's greater than 1.9, that's an ionic bond. It just transfers. So, how do you classify the polarity of a molecule? We have to look at the polarity of the individual bonds and the overall shape of the molecule. Nonpolar molecules generally have no polar bonds, or individual dipoles that cancel. We'll look at those. So if I look at CO2, remember CO2 was linear. It said that was linear. So that was a shape. Between this carbon and this oxygen, there's a dipole. Remember we said the oxygen wants the electrons more than the carbon. So it's pulling this way, and we see this arrow with the little crosshatch here. So this end is partially positive, this end is partially negative. It points to where the electrons are going. So it's being pulled to the left. On the right side, we have this carbon-oxygen bond. It is also polar. So this oxygen is pulling the opposite way. So even though both bonds are polar, if they're both pulling like a tug of war from opposite sides, what's the net effect? Zero. So even though the bonds are polar, the molecule is nonpolar. That has to do with its shape. If we look at water, oxygen is more electronegative than the hydrogen, so the oxygen is pulling. Remember, water is bent shape. So the oxygen is pulling. These aren't opposite each other. So when it pulls, it's not going to cancel anything out. So it's going to, you figure if tug of war, you can almost see the molecule moving. So water, the bonds are polar and the molecule is polar. Never ever forget water is polar. The north and south poles are made out of water. So that's why the shape is important. When we get more into chemistry, things like solubility. The rule of thumb is like dissolves like. Polar compounds dissolve polar compounds. Nonpolar compounds dissolve nonpolar compounds. Oil and water don't mix, unless you know how to do it. So, here, formaldehyde, the carbon-hydrogen bonds we said were nonpolar because it has an E and D difference of less than 0.5. Here we have a carbon-oxygen bond. So it's pulling. So even though this is trigonal planar, it's polar. If I were to look at BF3, also trigonal planar, the fluorines are pulling, but they're all pulling equally in opposite directions. They all cancel each other out. So even though the bonds are polar, BF3 as a molecule is nonpolar. We move over to ammonia. Again, we have 3. The nitrogen's pulling, but those hydrogens are in a different plane. Remember, ammonia is trigonal pyramidal. So ammonia is also polar. And if you look at CH2Cl2, the chlorines are pulling, but they're not opposite each other. They're 109.5 degrees apart. So this is a polar molecule.
How do you know which molecule molecule is gonna be?
You have to know the electronegativity differences, see which one wants the electrons more. If I were to make CCl4, carbon tetrachloride, now I got chlorines evenly distributed around the carbon. So even every carbon-chlorine bond is polar, but since they're evenly distributed, symmetrically distributed, they all cancel each other out. So carbon tetrachloride is nonpolar. If I were to replace one of the carbons with a hydrogen, now it becomes polar.
So if it's
Two of the chlorines with hydrogens, it's still polar, because it's not symmetrical. Three of them with hydrogens, it's still polar. If I go to the last one, now it becomes nonpolar.
Yeah.
Everything cancels out, it's symmetrical. It makes a huge difference in the physical properties of the compound. Trust me. Okay. Let's do a couple. You can tell me if they're polar or non-polar. Let's go back to SO2. How many valence electrons?
18.
So we have 18 valence electrons. All right. Okay. So ultimately, you're going to end up with what shape is this molecule going to be? How many groups are on the sulfur? Try again. 3. 1, 2, 3. How many of those groups have atoms attached to the ends? 2. What did I say? 3 groups, 2 atoms, 1 lone pair. What was that shape? What? Bed. That was the one that was added to the table. So now we have a molecule that looks like this. Which is more electronegative, sulfur or oxygen? Oxygen. So these SO bond and the S double O bond are going to be polar. The oxygen wants the electrons. Is that going to be a polar or nonpolar molecule? Polar, because the oxygens aren't opposite each other.
Does the one that has the double layers, is it full harder? Or is it maybe?
Well, remember, it actually flip-flops back and forth, so it kind of evens out. All right? So now, CO2 we said was linear, and it was nonpolar. Okay. What shape is this? Hydrogen cyanide. Linear. Two groups. But, what?
They would be linear, but is it polar or unpolar?
Well, that's what I asked him.
That would be,
It's linear. It would be polar.
That's polar because
Polar more to the next.
nitrogen is more electronegative than carbon, so I got something pulling this way, and I don't really have anything pulling this way. So they're not symmetrical, so this is going to be polar. So just because something's linear doesn't mean it's non-polar. You're looking for symmetry too. This isn't symmetrical. So hydrogen cyanide is polar.
the sulfur dioxide is polar as well, right?
Yes. Pretty much anything that's bent's going to be polar. TCl3. How many valence electrons?
Well,
26.
oh, 3.
26. All right, chlorine's in column 7. 7 times 3 is 21. Phosphorus in column 5. 5 and 21 is 26. All right, P, Cl, Cl, Cl. Next step, bonds. Next step,
Double bonds.
no, octets.
That's it.
Why do I give you a list if you want to follow it? How many electrons have we used? 24. How many got left?
2.
Where are we going to put them? What shape is this going to be? Trigonal pyramidal, yes.
Yes.
We have 4 groups. 1, 2, 3, 4. 3 of them have bonds, 1 of them lone pair. Pyramidal. So it's going to look like, actually it's going to look better than what I draw, but which is more electronegative, phosphorus or chlorine?
Chlorine.
I'll go with that. All right.
I
Yeah.
get a number to 1.
Chlorine is because it's more to the right. So we're going to have polar or non-polar?
Polar.
Polar.
Not balanced. It's one way.
Remember, it's not planar. It's trigonal pyramidal, so those chlorines are all below the nitrogen. So they're all pulling down on the nitrogen.
Why is that triangle there?
This? Oh. That's the way, what that means is, if I look at three-dimensional structure, the electron pair is even. This is even with the board. This Cl is coming out at you. The dotted line means the Cl is going back. That's the way you draw three-dimensional structures on a two-dimensional board. Well, that's the way the chemists do it.
Oh,